All right, so we're talking about today the bear lab. Okay, we're trying to, I call it the bear lab or the aspirin lab. We're not going to titrate bears, that'd be kind of crazy, but in any case. What we're going to do, like we do with the Tums labs, is this quality control lab. So what we're trying to do is verify if these tablets have 325 milligrams of aspirin, which is a common industry name for salicylic acid, okay, which has been around over 100 years as a common medicinal drug or pharmaceutical or over-the-counter medication. It's been called the wonder drug for the many uses and many benefits supposedly it gives. Although of recent years, this drug actually isn't the wonder drug it says it is, as they're finding out that it causes potential bleeding and ulcers of the stomach if there's overuse. Okay, so that's kind of interesting when you talk about how it works biologically and chemically. Any case, so just like your Tums lab, we're trying to verify what it says on the container. But before we get started, I want you to recognize that in our lab, in our Tums lab, and I will post these. I forgot to do it for the weekend, and I'm sure you didn't do much on it because you had something else to do. But if I just read over the milligrams of Tums that we verified on a 750 milligram, okay, tablet, or 750 value here, the extra strength 750 there that we got. I had 785, 777, 813, 747, the only one under by a little bit, 841, 906, and 887. So as the collective group, all of our tablets were a little bit above the 750 milligrams that we suspected, or at least that we tested for. Obviously, the label says 750. That, as a holistic group, leads me to believe that we are a little bit above. I'm confident that you guys did the lab accurately. I watched. So I'm confident the results you got, but what kind of, again, limitations did our experiment have to make us all be a little over? Could it be that the tablets of Tums had more calcium carbonate per tablet in the group that we have? Absolutely. Absolutely. You know, they make these in big, big vats, and maybe we got the bottom of the container that this package was made up of, and there's more calcium carbonate that's settled in that mixture. So don't think that all, 100% it's that we all had errors. It's kind of cool to me that all the data is moved above, okay? It means one of two things, that we're all collectively accurate together, or we're all collectively had the same type of experimental errors, which is kind of cool. We have to figure that out. We don't know for sure, but try to, when you write your conclusions, think of some logical reasons for and against. Any case, unlike the Tums lab, which I know they don't put a lot of effort into making sure every tablet has the same amount of chalk, calcium carbonate, they do so with aspirin. So I suspected that we would get numbers. I was very happy that we're around 750, but there is a lot of range here. 747 to 906 is our range. It's a big range. But I do know that there's no way that they're going to quality control every tablet for chalk. If there's more or less, that's okay. Pop in another chalk tablet. You're not going to have to go to a special place and talk about your troubles with Tums, okay? Aspirin's a different deal, okay? This was $8.50, although expensive for chalk, okay? This right here was, I don't know, $12.95, a lot more expensive for a lot less, okay? So what's the difference? Well, hey, if I am giving you an over-the-counter medication like aspirin and I'm a doctor, I want to be able to prescribe it knowing that the company that I'm using, hey, get Bayer, I know that they quality control that tablet to 325. So you better believe they're spending the extra time and money to make sure that this tablet, okay, is or has 325 milligrams of aspirin. Okay, so I would suspect in our lab that we're going to get much, much smaller range of values, okay, here. And I would suspect that we're going to get close to 325 milligrams per tablet. Okay, only because they put the time and effort. Why? Because they want doctors or hospitals to use their product because they know exactly how many milligrams. It's just that simple. It's about money. Okay, so the major objective in this lab is to quality control this Bayer product. okay, which has been making aspirin for many years. So in any case, what is aspirin and what are we trying to do? We're trying to figure out how many milligrams. So what is aspirin? Aspirin is salicylic acid. And in nature, it comes out as salicylic acid. And I want you to understand that this diagram here, if you remember your AP Bio, we haven't done a lot of this yet, but if I was to draw this ring, it's called a benzene ring, okay? You should remember that your rings, the corners of your rings are your carbons, right? So if I'm drawing this, the carbons go in those rings. And if you remember, carbon makes 4 bonds, so you're showing, they're not showing the H's, they're just simplifying the organic structure, if you remember your organic chemistry there. Okay, so it's really important as we look at the simplified structures of these macromolecules. Now, salicylic acid has been in nature and has been known to have medicinal purposes for many, many, many centuries. Okay, medicine people, women and men, okay, have been taking the bark of willow trees and through a couple of different ways obtaining the salicylic acid from them to give people that anti-inflammatory or anti-pain relief, okay? Problem is, anytime we've taken salicylic, if we take straight salicylic acid, it does upset our stomach. There's something about its three-dimensional structure that upsets our stomach. So one of the innovations that Bayer had, I think over 100 years ago, is that they added an acetyl group, okay, to this OH. So they added a little ester here, and acetyl salicylic acid is how it exists. So this is more palatable in our stomachs, having that acetyl group. So they added a little group there. And that's what we're gonna have to break down a little bit. So salicylic acid, hey, it's from the bark of willow trees. And it has the same medicinal purposes as acetyl salicylic acid, but this is more palatable. And Bayer was very famous in providing that little change to the molecule to make it more useful to use. Why take something that's going to make you more sick, right? Okay, so what does aspirin do? What does acetyl salicylic or salicylic acid do? Well, in the long story, it's been used forever, and I'm not here to get into all the specifics, but we do know that when there's pain or trauma, okay, there is these signals, and these signals from white blood cells who are usually in the area of the trauma, they give these signals, and these signals are progesterones, okay, prostaglandins, okay, and you should understand that NSAIDs are just a fancy way of saying non-steroidal anti-inflammatory drugs. If you ever had to be on steroids because you had to limit inflammation, normally it takes fluid from one area and moves it to another area. I know that my own poor wife had to be on them for a while for a condition, and she hated the pictures that she was on these steroids because they had these chubby cheeks. I thought they were cute. She hates them, okay? But any case, it's not very safe to be on them for very long. So NSAIDs, non-steroidal anti-inflammatory drugs, were a new form of drug that was safer in the long term, okay? But in any case, pretty complex thing here, but the bottom line is that when a white blood cell, a macrophage, or in this case a leukocyte, all right, understands their stress, and of course stress is released by you cutting blood vessels, different types of signaling proteins or chemical signals are released, but one of the things that happens is the white blood cells, whether they be macrophages or T or B cells in this area, they produce these prostaglandins that are important in the signaling of that pain, that contribute to the pain and the inflammation response. Pain, of course, is a receptor, okay? It's a nervous ending. And nervous endings work usually by pressure, right? Pressure, you put pressure, and if you guys learn your AP Bio, by applying pressure, you're changing the proteins that are, these transmembrane proteins that are on the membranes of your nerve cells. By putting pressure on them, you change the shape to their opening, ions can get through. And those ions get through and they cause that, that little pulse of electricity you guys called last year, that action potential that sent the signal to your brain that something's wrong. And they give off the pain response. Well, prostaglandins, what they do is, to help signal that, is they draw blood into that region for a couple different reasons. For the pain signaling, and number two, to bring in more white blood cells. So there's a whole, there's a stress that occurs in the white blood cell that leads to the production of a protein that turns on a transcription factor that eventually produces these enzymes that will convert a substrate into these signaling proteins very quickly that will bring and flow in blood into the area. And of course, pressure and blood come in. What's that going to do? Well, it's going to, by putting a lot of fluid in one area, you have more pressure on those what? Those nerve endings release, of course, you've got your pain. So these prostaglandins, okay, are involved in doing that. So cyclooxygenase, COX, okay, gets inhibited by these NSAIDs, okay, particularly aspirin. Its three-dimensional shape actually will block the COX's active site. Remember that last year, the competitive inhibition that proteins have? They have an active site where they're able to accept substrates and help catalyze reactions, but if something jumps in that active site, it stops the production of something. In this case, aspirin blocks or gets right into the COX2 active site. It's a competitive inhibitor, and it stops the production of this chemical signaling, which doesn't allow blood flow to occur, and therefore decreases the inflammation, and number two, takes away some pain. Okay? Now, there's a positive side to that, and there's a negative side to that. So these are different types of them. Thromboxane is the formation of clotting, which is important, narrowing of the blood vessels. Okay, so when you inhibit that, that leads to less blood clotting and leads to less inflammation, meaning the blood, you don't have that constriction of your blood vessels that close down. So you don't have that, and of course you have less inflammation, because when you have more blood flowing to an area, your blood vessels dilate. They open up so more blood can get there. Sprain your leg, or you have a cut or an infection, more blood's going to flow. And of course, we want to be able to blood clot. So by stopping that, you stop the production of these two different types, and it leads to less blood clotting. So one of the uses of aspirin is called a blood thinner. Someone who has high blood pressure or has the, the risk of having a blood clot will take aspirin because it prevents the production of clotting. Not so simple to explain down a major kind of kinase reaction pathway, all right? But same idea. And then of course there's this other one, prostacyclin, which reduces the blood clotting and dilation of blood vessels by stopping that as well. So aspirin blocks these two, and it lowers the body's ability to counter thromboxane, and there's less dilation. But there's a negative to this, okay? By allowing less blood flow to your injury, that's a positive thing. You're not going to have the pain and the swelling. But it doesn't just do that there, it does it everywhere. And we have less blood flow that goes to our stomach. And that causes a problem. We don't produce the mucus as well. We know that we have these parietal cells that produce hydrochloric acid, which is part of what? Breaking down proteins. But we also have what? We have to have mucus that lines. Mucus is made of a hydrogen carbonate. By the way, the bicarb is basic. So this actually lines our stomach in a mucus that's produced by the foveolar cell, I believe. And so this accepts a what? An H+, and this becomes CO2 and water as well. So this is a base, the bicarb ion, okay? If you stop the flow of blood to the stomach, that means there's less water the stomach can use, there's less mucus the stomach can make, and the stomach is susceptible to not having enough mucus. And there's not enough base for the H pluses that exist, and you could actually eat through your own epithelial cells and have bleeding in your stomach. So overuse of long-term use of these NSAIDs, especially aspirins, has led to a bleeding. So the wonder drug that it is now being said, used with caution. Okay, so that's some background here, okay? And I'm not here to give you that kind of lesson, but you should know what we're dealing with. Okay, so what are we after here? So when we look at this, I want you to think about this. Organic acids have what we call it, I call a COO group, C-O-O-H, right? A COO group. What's a COO group? Well, it's a carboxylic group, okay? It's where you have a carbon double bonded to an O, single bonded to an oxygen, and then bonded to an H. We've seen this before because this was an acid that we titrated. This is a weak acid. Anyone know what this is right here? It's an organic acid. It's weak. It was one of our titrations. It was our first weak acid, strong base titration. This is vinegar, or as we say in West Ham Beach, vinegar. Vinegar. This is vinegar, acetic acid. Okay? And it only 5% dissociates. It's got a Ka that's really small. So the question is, why do all organic acids have this carbon double bonded to the OH? Well, it's because, hey, very simply, if we blow this up, there's a pair of electrons here between the H and the O. Having two oxygens, both of these oxygens will cause this pair to drift a little bit. And that's why the H can slough off as H+. So it's a common functional group to see. So whether it's in vinegar or any carbon, hydrogen, oxygen, organic base molecule, you'll see that structure. We know it's an acid. And of course, we see that in acetyl salicylic acid, or aspirin. So taking a look at it, okay, we can see that we have this COOH group. It's how they draw it. And we have something that doesn't. But more importantly, you need to understand a reaction here. So this is important, okay? Now, if I look here, this is a carbon. So don't draw the carbon. So every corner is a carbon. All right. So again, this is really important. I'm going to blow this up a little bit bigger. But we have an issue here when we're going to deal with this acid, okay? So let's continue here. Okay, so when we deal with acetyl salicylic acid, we're going to have to hydrolyze this acetyl group that was put on there to make the aspirin more palatable. Okay, so we're going to add a base. Now, I know the base can rip off this H. Yes, it's acidic right here. There's a COOH group. There's your carboxylic acid group. Now, the hydroxide ion also wants to attack this carbon, and it pushes a bond on and makes this negative. That's exactly what just happened here. And this is rapid equilibrium. So this kind of goes back and forth. So what we're going to do with our acetic acid is we're going to add a strong base. It's kind of opposite of Tom's lab, where we crush the tablets and we figured out how much excess acid or total acid we want to add to drive it to completion. Well, we have an issue here. The issue here is the hydrolysis of the acetyl group. I add some hydroxide, it's going to go back and forth. So I have to make sure I have enough excess. Now watch, the hydroxide attacks. Remember, hydroxides, OH minuses, strong bases, break bonds just like H pluses do. Now, hydroxide comes, it brings a negative here. This is an intermediate. This next step, if it doesn't go backwards, can go forward, but very slowly. Think with me for a second. This goes back and forth quickly. It's a fast equilibrium. So this usually isn't around long enough for this to happen. So what we're going to do is add excess hydroxides by Le Chatelier's principle, drive it to enough here so that this next step can occur. What's the next step? Well, water with its positive proton, this negative rips it away, and the H comes back. And I know I should draw this here, but, okay, so an H is bonded here. This H moves here, okay, and we break this bond. So remember, hydroxides push their electrons on, and eventually they break a bond. And what we have, party people, and people that want to go to the party, including Zoe, hey, okay, we wind up cleaving this acetyl group here. Okay, this is called a reaction mechanism. I'm not holding you accountable for it, but I want you to understand that we're dealing with this issue of a hydroxide, and again, in the first part, let me just get my little pointer here. So I have the hydroxide, starts this process, and then gets re-kicked out, and what we make is our salicylic acid. But more importantly, it broke this off into a what? What is this right here? What is this H acidic? Isn't the C double bond to an O a C to the OH? Isn't that my, it's gone, okay. Isn't that my acid functional group? And I still have one here. So the hydroxide that I add winds up being re-kicked out. It doesn't really get consumed, so it's a catalyst. We'll talk more about that later. And then when I'm done, I have these two components, and there's how many acid groups now? 2. That's important for your stoichiometry. So by trying to neutralize the acetyl salicylic acid, aspirin, a lot to say there, I wind up with 2 hydroxides to neutralize. And there's my overall reaction. Okay, I need 2 hydroxides because essentially, anyone know what this chemical is right here? I just drew it. Carbon double bond to the O, to the OH. That's vinegar. So when we cut this off, it becomes the vinegar and an OH group. So I wound up with 2 parts, 2 acidic components, and we call this the hydrolysis, okay, of the acetyl group of aspirin, okay? Remember hydrolysis, the opposite of dehydration synthesis? Water comes in to do this. Okay, so it's important you recognize that we have a 2-to-1 relationship here. Okay, now this causes trouble for our lab. Okay, so one of our first steps is we're going to crush our tablets. We're going to take those, we're going to do 2 tablets. We're trying to verify 325 milligrams. And we're going to put that in a mortar pestle. We're going to transfer that to a beaker. But this time we're going to add, not water, but about 50 milliliters of ethanol. Ethanol has a strong non-polar characteristic to it. This, what we call a benzene ring or an aromatic ring, is very non-polar for, remember, your polarity in AP Bio. Anytime you have carbons and hydrogens only, it's a hydrophobic region, which means water doesn't have a way to really H-bond or attract it. So this does not dissolve very well, okay? Another reason why we put this on, or Bayer did initially, we put an acetyl group, but it makes it more polar and dissolves a little better. Okay, any case, so what we're going to do is take our aspirin tablets, crush them, transfer that to the beaker very carefully, okay, which by the way, is that a human error, transferring that? It's an experimental error. So people say, can I say that there is a possibility of not getting all the crushed tablets into my other beaker? Sure, that's an experimental error. The only way to not have that error is have this big container with us with big suits on, and we're crushing the tablet in that container, and then pouring the liquid on us and everything else. That's just not reasonable to do. So that's not a human error. It's an experimental. We have that, when you're crushing a tablet, you could lose some of that dust, sure. Make sure you use your water spray bottle. Okay, so in any case, what we're gonna do is we're gonna add it to some ethanol. So ethanol has also a hydrophobic component to it, so it's going to dissolve it better. And then we're going to measure out a certain amount of hydroxide with excess. And we're going to drop that hydroxide on there and let it mix. The problem is we need to get to the component where this completely runs out. So what we're going to do is add excess hydroxide. Why? To drive it this way. And we're also going to heat this, okay, to drive the reaction to this component here. That's going to take about 15 minutes, and that is well worth it. We've got to heat it, mix it, okay, with the excess hydroxide. If we go too fast, we're not going to get all of the what? Acid components. I've seen some people who didn't take the time to add the excess, heat it, and mix it properly, and when they're doing their final titration back, oh, they're neutralizing, and then all of a sudden it gets more acidic on them because this is still happening, right? We want to make sure we drive all the acetyl salicylic acid to these 2 components. If you don't, and it's still warm, this will still happen. You'll be adding some acid components that are not in your beaker, and all of a sudden I neutralize, and all of a sudden it goes back on you. Okay? So, I'm going to go over this again. We're going to take our 2 tabs, we're going to crush them, transfer them to a beaker. We're going to add about 50 milliliters of alcohol, ethanol, and we're going to stir, okay, for about a few minutes. We're going to add that to water. Ethanol is miscible in water. It can H-bond, even though it has a strong nonpolar component. Then we're going to add some 100 milliliters, 200 milliliters of water to that. We're going to add in phenolphthalein. What's the color? I'm going to add phenolphthalein to this mixture. What's the color? Turns what? Pink in the presence of, its pKa, if you remember, is what? 9, 10, 9.1. So it's going to turn color around that pH. So it's going to be clear because we're going to be in an acidic solution. Okay, now we're going to drop extra base on it. It should be now what? So we take our 2 tabs, crush them, put them to a 600 milliliter beaker. We're going to add, to a small beaker and have it dissolve in the 50 milliliters of ethanol. And transfer that into a bigger beaker. Okay, use your wash bottle, make sure we get all the drips and drabs out. And the next step is we're going to add some water to that. Okay, add some phenolphthalein. It should be clear. Now, I'm going to stir it. Now I'm going to carefully measure out the whatever arbitrary amount of extra base. I'm going to add the base to it. It should go what color now? Phenolphthalein will turn fuchsia or pink at a pH of about 9. It should go pink. Now, if you did not add enough base over time, what's this color going to go? I've seen this happen where people didn't calculate the right amount of base. And so they thought they had enough base, but over time, what's happening to this? It's making 2 acidic molecules, and all of a sudden it goes clear on them. And there's nothing to titrate back. You've got to add more than you expect. So I've seen this problem. So we add the phenolphthalein, we have it in the water, we have it dissolving, okay? And the phenolphthalein is a guide. It should stay pink during this process. If it didn't, you didn't add enough base as this is happening and more acid is showing up. But now, very important, to help this out, we're going to heat as well. And you can't heat a solution with alcohol directly because there is a flash point of the alcohol. So what we're going to do is make a water bath, and I'll help you with that. But a water bath is nothing more than a beaker. Okay? You heat in the water. Here's your hot plate. And we're going to suspend the beaker here. And the water can only get so hot. The limit that water can get, anyone? At 1 atmosphere? It boils at 100. Can't get any higher than 100. So we're going to heat the water less than 100, but there's a limit to how hot water can get. The surface of the hot plate is really hot. So we're going to prevent overheating, okay? And then we're going to take it off and what? Mix, heat, mix for 15 minutes. Watching the phenolphthalein color, which should stay what? Pink. To show us that we have what? More base than acid. If it goes clear, we did something wrong. Now, it doesn't mean we're done. We can figure out how much more what? Base we can add. All right? Are you with me so far? That's the tricky part because of this, this reaction here. All right? So, let's get started with our design. All right? So, what's the target? The target is 325, yes? So, how many tabs are we going to do? Notice I'm cool today. With the video, I'm cool. It's tabs. All right? Yeah. All right. So, we got 2 tablets. I can't last. So, if I'm using 2 tablets, what's my target amount of acetylsalicylic acid?
750.
Or 650?
Or 6, oh my God.
That's okay. It's okay. Don't be afraid to yell out, okay? That mistake forever is captured on my video, which I'll post every year. And I won't mention it's Adam that did that, okay? All right, so 650. And that's gonna be 0.650. I'm probably gonna make a mistake in this next second, so it's even worse for me. You're not even on camera. They don't know it's Adam P. Okay, now, so 0.650 grams. I'm not gonna write the chemical formula because it's getting too, I'm gonna write aspirin or ASP, not for a, what can I say? In any case, we'll do aspirin there. And we're gonna convert to moles. 1 mole is how many grams? And I did give you the molecular mass is 180.158. A little tidbit of information, glucose is also 180, kind of cool, maybe not. All right, but in any case, 1 mole is 180.158 grams. And this is what we're doing here, party people. Okay, we're gonna get rid of aspirin. For every 1 aspirin, how many hydroxides are needed? For every 1 aspirin, how many hydroxides? Anyone? Ferris Bueller, anyone? There's 2. Right there, party people. We're gonna, at the end of this, we're gonna have 2 acid groups. So there's 2 hydroxides. And what's this gonna give me? A mole of hydroxides. Why is that important? Well, party people, we want to completely figure out what the target amount of moles of my aspirin is. Okay, which would be this. Okay, this is my aspirin. And anyone get a number for me? So 0.650, this is the first thing we do. Divide by 180. Times 2. I get 0.007, everyone's afraid to make a mistake on camera. 0.00722. I'll just do it myself. Okay, so that means I have 0.00722 moles of hydroxide exactly needed to neutralize my aspirin if, in fact, each tablet was 325 milligrams. Remember, we're using 2 tabs here. Of course, why do we have to do a back titration? I've got a tablet. It's not soluble. I gotta crush it and expose every single aspirin to the base. And I wanna drive this, what? This reaction here, this equilibrium forward, okay? To expose both acidic portions. So I'm gonna add an excess. Here's the question. Arbitrarily, I've been telling you guys in the past, you decide what that excess is. Okay? But I'm going to help you. Okay? Because I just think you guys got a lot going on, and I don't want to spend 2 weeks doing this. Okay. So I'm going to add 0.01 excess. All right? So 0.01 excess. And you say, well, why am I choosing this? To be honest, in the other class, I chose a bigger value. And then when I figured out what the base had to be, then it was too concentrated. So this is, I think, safer. So the total amount of moles of hydroxide is going to be what? 0.01722. Listen, I love it. You're out here trying to answer a question, taking a risk, taking a swing at life. Sometimes you strike out in front of a video. That's embarrassing. Okay, Liz, I'll never mention your name on the video game. Okay, now. Nobody's going to answer any question from this point forward. Okay. All right. Now, that is the moles of hydroxide total that I want to add based on that target. This looks a lot familiar, doesn't it? Okay, we're almost done today. Okay, and I will give you a break because we worked through it. All right, bless you. Now, the first thing I want to do is I want to figure out what the amount of, or the molarity of the base you guys are going to make. Although I'm helping with the arbitrary values, you're going to make these solutions. Okay? And unlike the lab that we previously did, oops, let me get my flask. unlike the lab we previously did, we were talking about how much for the class. But here you guys are gonna make these individually. So you're gonna use something called a 100 milliliter volumetric flask. So every lab group is gonna make their own solutions. So unlike the 500 milliliter flask, volumetric, you're gonna use 100 milliliter. So you're gonna make what you need. It's important you understand how to do that. Okay, little guy. All right, now, so we wanna be able to figure out what's the solution I should make. All right, so a molarity formula. Not MV is MV, okay, moles over liter, of course. 0.01722 moles. I want to deliver that. I want to deliver those moles. 0.01722 moles. Okay, now here's my question. I want to do that over how many milliliters? You guys are going to make 50 milliliters. Every solution you make is maxed out to 50 milliliters. So you are locked in because I'm not making, you're going to make your own. That means you're going to add something, dilute to the 50 milliliter mark. I mean 100 milliliters, it's a 100 milliliter flask, I'm sorry. So how much are you going to make? Okay. Okay, so the biggest mistake is putting 0.100 there. Even though we're making 100 milliliters, what are we adding? A strong what?
Base.
And before I can even use it and do this back titration, don't I need to know exactly what that sodium hydroxide is? What's the problem with sodium hydroxide? It reacts with CO2 in the air. It makes sodium carbonate, which means when I measure it out on a scale, it's going to be heavier than I expect, which means I'll have a less of it. Something else that it does, anyone? NaOH is deliquescent, which means it absorbs water out of the air. It dissolves itself. So we're going to be dealing with the solid NaOH. It's very reactive. We need it to be reactive to drive the reaction forward, but the negative part, remember these are always compromises in science, is that it's going to react in the air. So no matter what, we're going to have to standardize our solution. So think with me, if I'm making 100 milliliters of my solution, should I be using 100 milliliters total of this to deliver 0.01722? No. Shouldn't I design this to be less than that? We're still going to make 100 milliliters of whatever we need, but let's think about this arbitrarily. How much do we want in our standardization? 10? Remember in the last, what did we do? Didn't we design this around adding 10 of our base into the burette? And didn't it wind up being 10.3, a little bit bigger? Because the base was a little bit weaker because it reacts with the components of the air that we just talked about? So we need to design this. Think about that. So this is important. This is the part where people break down here. This is important. I'm not going to put 0.100. Are we going to use 0.110? Sure. But I'm going to say, let's make it 80. So that I have 10 to 15 milliliters to put in my burette. Maybe rinse the burette a little bit. You should always rinse the burette with your titrant first a little bit. So I'm going to make the molarity 0.08 liters. Again, why did I pick that? We are going to make 100 milliliters of solutions. This is a 0.1 milliliter flask. We're locked in by that. You don't have anything else. I'm going to use 20 milliliters of that, okay, to either rinse out my burette or standardize. You have to standardize this with KHP. So let's go find that molarity. 0.01722, and I'm going to divide by 0.080. And I get a molarity to be 0.215. Of NaOH. That is the molarity I need if I'm going to use 80 milliliters to do this. So what's that tell in your head? You're going to measure exactly 80 milliliters of this solution that how much you're going to make? How much do you have to make? Do I have 80 milliliter flasks? No, I have hundreds. So you're going to make 100 milliliters of that molarity, but measure out 80 of it to put into the sodium, the crushed tabs of aspirin and the phenolphthalein and the alcohol, methanol, I can speak. Okay, so it's important. Let's go find the next piece. Okay, so that's our molarity we need. Okay, how do we make this solution? I'm going to give you solid sodium hydroxide pellets. Well, that's my molarity. Okay, and I want to solve for moles. Again, molarity is equal to moles over liter. How much do we want to drop into this container? Oh, sorry. How much do we want to make? 100 milliliters. What's the molarity? 0.215. Let's solve for moles. Now I could do this in one step, pretty dimensional analysis, but I'm not today. I can do this in half. Times it by 0.1. Okay, so we get 0.0215 moles of NaOH. Convert that to what? Grams, right? 1 mole is how many grams? You've been to the molecular mass party? Aspirin is 180, glucose is 180, CO2 44, sodium hydroxide 40. You guys are missing a lot of parties. Nobody shows up. But we could be memorizing stuff for no reason. Okay, so 0.0215 times 40, and I get 0.86 grams of what?
Sodium hydroxide.
Okay, and what do I do with that? I'm going to carefully take the weighing boat, put it on a what? Scale. I'm going to tear it out. What does that tearing mean? Hit re-zero so that the scale thinks the container is part of the scale. You're going to carefully add 0.86. Now these guys come in tablets, so you're going to have to use a mortar and pestle again to crush the tablets and small enough to exactly measure 0.86. You're not going to sit here and get something close. Exactly 0.86. Then you're going to add it to your volumetric flask. Carefully, every tiny little piece. Use the wash bottle to make sure that all comes in. Add about distilled water half the way. Pre-dissolve. Why do we pre-dissolve? The solid is yes.
Because the volume changes. As
Yeah,
it dissolves.
the space that the solid is displacing as a crystal is different than it would be as an ion. So you just can't fill it up to the line. So we're going to pre-dissolve it. It'll get warm because it's an exothermic reaction. And carefully, with distilled water and a pipette, we're going to get right to the gray line. Spend the time, because these labs, which are titrations, we're trying to find milligrams of something, are all based upon the accuracy of your molarities. Completely dissolve it. Label it. Put a date on it. Okay? And that is the first half of the lab. Now what do we have to do next? We're going to have to standardize it. Oh, but remember, I only need what? Part of your procedure, how much of this are you going to add to a graduated cylinder and carefully measure? 80. We still have 20 to play with to do what? Rinse our burette and standardize. Okay? Tomorrow we'll talk about standardization, which we should calculate the standardization necessary, and some other things, and that's the first half of the lab.